Hello, sixth grade. This is a quick review movie for your astronomy quiz coming up on stars in the galaxy. These are the 6-3 notes, but they should be exactly the same, look almost exactly the same as the 6-1 notes, so you both can use them. So I'm going to go through the notes here just to do a quick review. All right. So the first page here. Remember, talks about where we are in the universe. This is very important to know, and it helps put things in perspective to know that we are here on the Earth next to the Sun, and that's part of our solar system. Our solar system surrounds one star, the Sun. That star is one of a billions of stars in our Milky Way galaxy. Our Milky Way galaxy is just one galaxy in our cluster of galaxies, and that our cluster of galaxies is just one of billions of galaxies in the entire universe. So this sort of shows that how things are in perspective in the entire universe. That video that we watched that showed the person sort of zoom out from the people having picnics helps sort of show this idea. So this is pretty important to remember. All right, so when we think about, well, where is the universe coming and going, one thing to think about is the Doppler effect. And we talked about this as how an observer might observe either sound or light if the thing that creates the sound or creates the light is moving towards you or away from you. In sound, it can make the pitch of the sound change. For instance, if a siren on a car is driving by you, it'll sound high at the beginning and then low when the car moves by you. The same thing is true with light. If there is a light source that's moving towards you, the light actually appears more blue. It's sort of called a blue shift. If the light is moving away from you, it creates what's called a red shift. And this is pretty important because Edwin Hubble, different galaxies, noticed that there was a red shift in all the galaxies. That means that they were moving away. So we realized that, whoa, all galaxies are moving away from everyone. So if everything's moving away from everyone, it must have mean that they all had started at an original place. So just like ripples in a pond, if all the ripples are moving away, there must have been a moment in the past when they were all together. So this theory is called the Big Bang, that the entire universe started from a single point and since then exploded out and is continuing to move out over into the extent of the universe. All right, so then thinking about stars and how far away they are. And one of the things they can think about is how much light they give off and how much light energy we see here on Earth. And so the two things to distinguish about that is absolute magnitude, which sometimes we also call absolute brightness. It's the same thing. The absolute magnitude or brightness of a star is how much light energy that star actually gives off. All right, so like a big bonfire gives off more light than a little candle. So you could say that the absolute magnitude, the absolute brightness of a bonfire, a big fire, is more than a little candle flame. The apparent magnitude, the apparent brightness, is how much of that light do we see here on Earth? And that can be different. For instance, if you have the candle right up near your eye, it's getting a lot more light into your eye than if that bonfire was far, far away, like on the other side of a valley, right? So the candle would seem brighter than the far, far, far away bonfire. Well, this is true with stars. If there are two stars, for instance, an example, giving off the same amount of light, they have the same absolute brightness magnitude, but when that light gets to Earth, the one that's farther away is going to appear more dim, so it has a smaller apparent magnitude. In this example, this star has a smaller absolute magnitude than this star, but because this star is farther away, they might appear to be the same distance from Earth. Galaxies. There are three basic types of galaxies: ellipticals, which are sometimes the oldest types of galaxies; irregular, which are weird shapes; and good old spiral galaxies. And spiral galaxies is the type of galaxy that we're in, the Milky Way. There's some examples of different galaxies. There's a picture of us within a galaxy. We're in the Milky Way galaxy. Now we talk about the different types of stars and how stars can change. This is on the HR diagram, which we'll look at in a second. The HR diagram sort of shows, well, I'll jump to it right here, that most stars, that the cooler they get, the less bright they get, but the warmer that they get, the more bright they get. So here's a star that's pretty cool, and it's also not very bright. Here's a star that's very, very hot, and it is very, very bright. So most stars, like the sun, fit this pattern. Not so hot, not so bright. Very hot, very bright. But a few don't fit in this rule. And these are the stars that are very, very hot. They're look on the hot side of the side here, but they're not bright because they are small. These are the white dwarfs. They're super hot but super small stars, so they don't give off a lot of light. On the flip side, there are stars that are very, very cool, relatively cool, 3,000 degrees, but they do give off a lot of light. They do have a very high absolute magnitude because they're so huge, and these are the giants and the supergiants. Now, to think about what types of stars these are, there are certain categories that define their temperature, and these are defined by letters O, B, A, F, G, K, M. And we'll see that those letters have to do with the spectral type. Those spectral types have to do with their color and their temperature range. So we can see that the hottest range is 25,000 to 50,000 Kelvin. That back here, here's the O range, 25,000 to 50,000. This is the hottest types of stars. But then O, B, A, F, G, K, M, those show that different types of stars can get cooler and change different colors. All right. There's also what's called the luminosity, but you can also think of this as the size. They use Roman numerals to decipher that. So the biggest stars are Roman numerals 1 or 2 or 3 or even 4. Main sequence stars have a Roman numeral of 5, and little dwarfs have Roman numerals of 7 or 6. And so using this information, and on the quiz you will be given this information. You do not have to memorize this. It's also on binder page 22. You can use this to describe certain stars by given what's called their spectral type. So if we saw our sun, which has a spectral type of G2 Roman numeral 5, the 5 means it's a main sequence star. The G means it's yellow-white. The G also means that it's this range of temperatures, and the 2 means that it's on the warmer side of this range of temperatures. The last thing to think about in these star notes is how stars can change and live over time. This has to do with two major things, two different sort of forces working against each other within the star. The first is fusion pressure, which is the exploding sort of fusion energy that's pushing a star to make it bigger and bigger and bigger. But then there's also gravity. Gravity is always working on the star to pull it in closer and closer and closer. And those two things are always working sort of against each other. And if they're balanced, the star stays the same size. If fusion pressure starts winning this sort of battle, the star is getting bigger. If gravity is more forceful, then it starts to win and the star shrinks in. So we can see that when these two things happen, we can have two different life cycles of stars. Now this is described in words for both a medium-sized star and a large star. But the best thing to look at is this page. So we start with the nebula, which is sort of all this dust and gas, and then it becomes a protostar, depending if it was a really big nebula to become a big protostar, or medium or small-sized nebula become a medium or small-sized protostar. The star then expands, gets bigger, becomes a main sequence star. It can expand even more and become a giant, and then it will shrink because of gravity and become a white dwarf, and then finally when it kind of goes out of no more nuclear reactions, it becomes a black dwarf. It's kind of like a blown out candle, so to speak. You could also have a big star sort of cycle, or a life cycle, where you have a big protostar, it expands and becomes a big main sequence star. It expands even more and becomes a big supergiant, but then you have this big supergiant, and all of a sudden, gravity takes over and boom, it collapses in on itself. It just collapses in. And when it happens, it releases a lot of energy. This is called a supernova. It's like the biggest explosion you can have in the universe. After the supernova is over, what's left is this sort of small, super small neutron star. And that neutron star might collapse even more to become the most dense thing in the universe, and that's a black hole. All right. The rest of the notes are sort of are pictures of nebulas, pictures of our main sequence star, the sun, and other pictures of actual things in the universe. But what we just went over are the main parts of the notes. Please take notes of your notes, and please email me if you have questions. All right, good luck, take care, see you later.